AGN feedback is the group of physical processes that connect the energy and momentum released by AGN with the interstellar and intergalactic medium of AGN host galaxies. Even though there are various candidate mechanisms for AGN feedback, such as jets, winds, and radiative processes such as photoionization and photoheating, we still haven't identified the dominant AGN feedback mechanism. In this talk, I'll briefly review the efficiency of radiation pressure on dust as an AGN feedback mechanism. The natural environment for this process is the high redshift universe in starbursting galaxies, where high dust masses and high quantum densities ensure that the bulk of the AGN radiation field can be absorbed by the dusty ISM. There are two separate regimes in this model. The first one is called the single scattering regime. This is when UV and optical photons are absorbed by the dusty ISM, but re-emitted infrared photons escape. The maximal force you can exert in this regime is L over C, where L is the AGN luminosity. If the quantum density is particularly high, it is possible for even the re-emitted infrared photons to have to be absorbed and re-emitted multiple times before they escape the optically thick region. Thus, on average, each photon will undergo more than one scattering, and since photons preferentially diffuse outwards, the net force exerted by multi-scattering radiation pressure can exceed L over C by a factor that depends on the optical depth. So multi-scattering radiation pressure can result in stronger feedback than single scattering radiation pressure, provided infrared photons can be trapped efficiently. We've performed a suite of radiation hydrodynamical cosmological simulations with the code Ramses-RT to try to measure the importance of single scattering and multi-scattering radiation pressure in powering large-scale outflows at redshift 6 in massive halos. We have targeted a very massive halo with a massive 3 times 10 to the 12 solar masses at redshift 6. This is where we think the first quasars formed, and we performed different simulations where we systematically compared the efficiency between only UV and infrared radiation pressure. We found that generally single scattering radiation is not sufficient to drive powerful outflows at realistic AGN luminosities. You can see this by looking at this plot. This shows on the y-axis the maximum outflow velocity, and on the x-axis the bolometric luminosity. And the blue data points show you the results from the simulations with only single scattering radiation pressure. What we found is that you can drive powerful outflows, but we need to reach luminosities which exceed 10 to the 48 ergs per second. These are much higher than the typical luminosities of redshift 6 quasars, which are marked with these vertical gray lines. Instead, once you account for the trapping of infrared radiation, we find that outflows can now be launched at realistic AGN luminosities consistent with the luminosities of observed quasars. Therefore, multi-scattering radiation pressure makes the difference between a strong outflow and no outflow at all in these redshifts. We've also looked at the internal properties of these large-scale outflows, and these plots show you phase diagrams. So on the y-axis, the temperature, on the x-axis, the density of outflowing gas in these simulations. This panel shows you what happens if there is no quasar and the outflows are launched purely by the supernova feedback. You see that most of the outflow is very low density and very hot. But remarkably, once you include the quasar radiation, you find that the phase diagram of the outflow starts resembling the phase diagram of a multi-phase ISM, such that there is outflowing gas which is very dense and very cold, some outflowing gas which is warm and ionized, and some outflowing gas which has very low density and very high temperatures, spanning more than 5 orders of magnitude, both in density and temperature. So these radiatively driven outflows are quite powerful, and they also multi-phase. We've also tried to look at the impact of these outflows on the host galaxy. And what we find is that they have a very modest effect on the star formation history in the short term. This shows you the star formation rate on the y-axis as a function of time. The green line shows you what happens if there's no quasar, and the other lines show you what happens when you add very bright quasars, the orange being a quasar with a luminosity of 3 times 10 to the 47 ergs per second. Even though the galaxy looks very different because the quasar does destroy high density regions, the star formation rate, when you integrate it over the entire galaxy, does not decrease that much once you include radiation pressure on dust. Therefore, the conclusions are that radiation pressure on dust can and does launch powerful outflows and can clear out the galactic nucleus. If you don't have infrared radiation pressure, this model probably does not work because you need very, very high AGN luminosities. These outflows are naturally multi-phase. They consist of a cold, dense phase, a warm ionized phase, and a hot, low-density phase. And we found that even though these outflows can be quite powerful, they don't really have a very strong immediate impact on the ability of its host galaxy to form stars. Thank you for listening.